Okay, this is the homework over Chapter 12 that was due today, which is November 29th. Okay, first reaction. We have a molecular halogen in water. We should be thinking about what that means it is that we're going to make exactly. Okay, but let's draw out the mechanism and just see how we get there. But this is definitely a reaction we need to know. Okay, we need to just know this by looking at this instead of always. We don't always want to draw the mechanism out. Okay, we should have this on our list of reactions that we should know. Okay, so we're going to start off making our halonium intermediate, right? That three-membered ring to the chlorine, which then has a positive charge. Right. And then we know, I'm just going to pick one of the enantiomers to draw. We know this chlorine, well, I guess it's not really even an enantiomer in this case, because, no, I guess it is actually, right? Because we can't, this is not cyclohexane. If it was cyclohexane, this would be a meso compound. But this is not meso. So this, right, we also get the other enantiomer as well. So we could say at this point this is racemic. I'm not going to label racemic again until we get to the end. Okay, but we know that this could be wedges or dashes. This chlorine could end up on either face of that pi bond. Okay, then we're going to attack the more substituted side. Right, remember we want to think about this being kind of like an epoxide opening where we have the positive charge on the oxygen under acidic conditions. Okay, the delta plus is going to be the side closer to the oxygen. That's the side we would consider to be more substituted because this lone pair from the oxygen can then have a resonance form that stabilizes that, growing positive charge on that carbon. It's not a full carbocation, but it's very carbocation-like. Okay. So again, we would consider that side with the oxygen to be the more substituted side. So that's the side that will get attacked by water, right? And that's going to cause this to just become a chloride. We know that we're going to have inversion where we opened that ring up. All right, so my my water has to attack from the back side. Give me this, and my chloride is going to my chlorine is going to stay here. Okay. So again, they have to add anti to each other, but we could have had the chlorine start as wedges, and that would have given me a dash here as well. So I guess I will just go ahead and write racemic through the whole thing, just so I don't forget. Okay. Then finally, to get my product, I need to just deprotonate this to give me an alcohol. Okay. So again, it's anti-addition of a chlorine and an OH. So we just get two products here, we don't get four. Okay, we just get a racemic mixture of this one diastereomer. We don't get the other diastereomer, and it's an enantiomer. Okay, 37, this is a similar one. This one also wants us to draw a mechanism. Okay, the key is we're using the same alkene and molecular bromine, but one of them is in carbon tetrachloride as a solvent, and one's in water. So don't forget the key difference between these two. Okay, when we have water, it's like the last reaction. We end up putting an OH on one of the sides of the double bond. When we don't have water, we just have carbon tetrachloride as our solvent. We add bromine across the double bond all the way. Okay. So again, I'm going to make my three-membered ring, and I can make this with the bromine on either side. So I'm just going to pick one of these ways to draw this. Okay, and then my bromide ion is going to come in and attack on the more substituted side, right? And that's going to give me, that's just going to take me all the way to my product. Now, in this case, okay, remember, they have to add anti to each other. Yeah, they have to add anti to each other. So when we draw this as adding anti, okay, I'm going to draw it like this. And then I have my two methyl groups and my bromine here. Okay, the way that what I would get from this way that I have it drawn would look like this, right? This would be an H. And this is an achiral carbon, but this carbon is chiral. Okay, so again, as always in this chapter, we're going to get a racemic mixture here. Okay, Now, if we do the same thing, I'm not even going to draw this whole mechanism out because I just did this on 36B, but we would expect to get the exact same thing, except, okay, instead of a bromine attacking this side with the two methyl groups, it would be the water that attacks that side. So we end up with an OH group that adds anti to our bromine. Okay, and then the rest of it's the same. So this is racemic. Okay, 42D. This is a little bit of a doozy of a mechanism to write out. So this is our lovely mercury mechanism. Okay, so just like all of these, we're going to start by making our three-membered ring. Okay, just like we do with many mechanisms in Chapter 12. So, and remember we said we consider this mercury to kind of have a lone pair because it's D10. Okay, so here's my first step, is just making that ring with the mercury. And as always, I can do this on either face, so I could put my mercury coming out of the page or my mercury going into the page. And it has a positive charge. Okay. Then water, just as with all these three-membered ring intermediates that have a positive charge, we're going to attack the more substituted carbon. Okay. Now, because this at the end is a CH2, I can actually really simplify the stereochemistry here, because I know, like I said, I'm going to add anti, right? And I have to add the water to this side, which means the H has to go on this side, right? Yeah, the H is going to have to go on this side. Okay, so I'm not going to generate a chiral carbon here. I'm only going to generate a chiral center here. And this could do backside attack and end up as a dash here, or if I had drawn this mercury ring with dashes instead of wedges, then this could have ended up as a wedge. So, long story short, okay, when I show this next step, taking all into consideration, I can really just say, okay, so here was my two carbons from before. This I can just draw as a line because it's not even chiral right now, right? There's two H's right here. Then this one, I will just pick one. I guess the way I have this drawn, I need to do this as the dash for the OH. Okay, but we just know that really what we generated here is a new chiral center. And it starts off as an OH2 right here, right? This is racemic. Okay, now my next step is just to take off this proton, so another water molecule can come in and do that to make just my regular old alcohol. And again, this is racemic, right? And then this is the last step that we don't actually have to show any arrow pushing for. We just say sodium borohydride and ethanol. We'll swap out this mercury for an H. And again, don't forget this is racemic, as all these pi bond ones are. They're not stereospecific. Okay, last one. This is one of these peroxy acid ones. Okay, this is what you had to kind of recognize. It doesn't have to always be metachlorobenzoic acid. It can just be any peroxy acid, where we have the cetyl bond O, OOH. Right, this is the peroxy part, this O to O bond. Okay, how to draw this. The way that I would start drawing this is kind of line up the O and H with your alkene. Because this O to H, right, this is the O that ends up making the epoxide. So I would kind of line that up with the alkene first, and then kind of draw the rest of it as though it was a five-membered ring, because that's going to make it the arrow pushing the easiest to draw. Okay, so you want to have kind of like 1, 2, 3, 4, 5-membered ring, kind of roughly in a pentagon shape here. It's going to be the easiest way to draw the arrows. Okay, now all of our arrows. we have to make the epoxide. Okay, so we definitely have to move this one to the oxygen that's going to make the epoxide. We know, I mean, if we want to just skip ahead to the product here, because honestly this probably makes it easier to think about the mechanism if we can just draw the product. Okay, I'm going to make an epoxide here, and as with all epoxides or all these pi bond things, I can make the epoxide from either face of this alkene. So this is going to be racemic. Right. This OH is not going to get changed. Right, so I could draw these as little dashes as well. Okay, so I said we're going to make an epoxide here. This is the O that makes the epoxide. So alkene is going to donate one of the bonds to make that epoxide ring. The other one comes from this O to H bond. Okay, which means that this H doesn't have a partner now. So everything else happens kind of as a result of that. Okay, this becomes this new bond between an O and an H. Okay, I could just show this, I guess, all the way attacking this H maybe is more clear. Okay, that's going to make a new bond. Then, because this is getting attacked, okay, it's going to have to lose a pair of electrons as well. So that's going to make a new double bond here, okay, which again causes this to come over and grab this H. Okay, so we don't end up with our H just kind of floating freely. And the result is you get just a normal carboxylic acid, right? Because all we did was transfer an oxygen atom to this. So really we're just kind of plucking this oxygen atom out of the middle and making this as our product. Okay, if you can remember those two things, it's a little easier to figure out the arrows on that mechanism without just straight memorization. Okay, just don't forget the 5-membered ring part as well. Okay, and that concludes the last homework key. So good luck on the exam. If you're watching this, if you have questions, send me an email. I'll do the best I can to help you out, and good luck.